really what I want to talk about in this talk is well, it's really focused on memory and the issues that we're having with memory. It's kind of funny if you look at a lot of the work that's being done in the space right now. It has to do with how can we make our applications more memory efficient, and really what's driving this is the fact that memory is slow. And it's not getting fast enough. Our CPUs are actually getting faster by a factor of 8% per year. And over time, the gap between the performance of memory and CPU performance is it's incredible. So you get to the point where if you're doing any type of memory access in your application, or allocating or doing a lot of things like this, then what you're actually doing is you're causing your CPU to stall, and it's stalling quite frequently. You get frequent stalls and you get long stalls. So you can stall for hundreds of clock cycles at a time. So you might make forward progress of like tens of clock cycles, and all of a sudden you're stalled for hundreds of clock cycles, and it's kind of like a real issue. Now, there's a whole other host of problems that this particular problem exposes, right? So, I'll ask this question, like, what is your performance trouble spot? And if you look at an industry survey, so this is a couple of years old now, but I still like it and I still use it because I don't think it really has changed that much. And if you look at it, the big bubbles are all to do with databases. They're all database issues, as you can see, right? And really, what we find here is the big problem is this one, right? It's basically the memory efficiency of your applications. As a matter of fact, if we look at data that we've collected from companies operating pretty much worldwide, so I get people sending me like garbage collection logs, and with garbage collection logs, I have the tools to do the analysis on the logs to actually understand what's going on. What we find is that approximately 70% of all applications are bottlenecked on memory. That is the bottleneck in the application, right? So if you look at the division in this room and stuff like that, you could say that all of you people here, all of your applications, about half of those people over there, all of your applications are bottlenecked on memory. It's like the people in the back, you don't have to worry, you can go someplace else now just to see another talk, right? So it's really that serious a problem. And no, garbage collection is not at fault. Garbage collection creates tail latency events, but it's not responsible for an overall level of latency that we're seeing in our applications now. So we get into this question, right? Okay, where does this come from? It's like a lot of the frameworks are responsible for inducing a lot of churn in our applications, so they're very memory inefficient. So on the other hand, a lot of these frameworks are very useful, and we need to use them. But we need to be aware of what their impact is, right? So the question is, do you Spring Boot? Is anyone using Spring Boot here? Right? Cassandra? Not so much. Spring Boot's popular, right? Or any big NoSQL solution database? Anything else? Got a few more hands going up for that. Anybody using Apache Spark? Right? Anybody in Scala? Yeah, there you are. So that's a problem right now. And of course, we're going to Kotlin. Anybody thinking about Kotlin? You can start, right? Or any other big data framework is in that fact matters that we see the same issues. Log4j. Who here is using like Log4j? Logback? SLF4j? JDK logging? Yeah, we got one even over there too, right? It doesn't really matter. It's like for any Java logging framework, the way they're written now, right? JSON? Anybody using any form of JSON and stuff like that? Yeah, who isn't, right? And the list of things like, go on and on and on. One of the strangest things we actually saw recently, ecom caching products, Hibernate, so on, and so on. Any of these things, you're likely in the 70%. So one of the strangest conditions we saw just recently was, excuse me, we saw an application where they actually decided to go off heap, right? They went off heap because they wanted to get rid of the tail latency issues that they had with garbage collection. But by going off heap, they had to do marshal data to get it off heap. They had to marshal data to get it back into heap. And so they have this barrier which basically says, you know, I'm in that space or I'm in this space, but I need to be in this space to do the calculations and everything like that. But the issue was they created so much churn because they're always taking the data on heap and off heap. They actually created a bigger problem with the memory churn than the problem that they had with the tail latency issue. And quite frankly, if we look at the problem that they had with the tail latency, it's quite likely we could have mostly tuned it out of their application with proper GC tuning. Right? So it's really kind of like one of these weird situations, right? So war stories, this one war story is like, you know, you look at it. When you look at the theme here, the theme is that when we start tackling this problem, this is when we get the huge performance benefits. So our internal JVM guys, where I'm working at Microsoft now, I basically said, okay, if we can improve escape analysis, we're going to get better localization of variables. With better localization of variables, we should get better allocation site reductions, which means we're going to take pressure off of the allocators. And in doing so, we should see some very significant performance improvements. And lo and behold, they started off on a path where they're just starting. They're already seeing like 10 to 20% improvements in performance for the same workloads. And in some cases, like with some of the Scala workloads, we're seeing upwards of like 40% improvements in performance. And where this is all coming from is just by reducing the allocation pressure of the application. And in this case, it's allowing the optimizers to do a better job. So right now I'm talking about this magical thing called an allocation site. So just to clarify what I'm actually talking about, we're looking at this thing as like foo equals new foo. And when we drop it down to bytecode, you can see we have a new and a dupe and invoke special. And really, this is the thing that forms an allocation site. Now, in highly localized variables, it's quite possible that the optimizers are going to look at this and say, you know what, I can just basically do a scalar replacement of this allocation, which means I don't need to do an on-heap allocation. So it's going to take a lot of pressure off the allocators when you can start doing that. But it's only able to do that under very special conditions. And the conditions are the variable has to be local. It has to be running within a local scope. And it has to be proven that only the thread that created that data can actually access that data. And if it fails that test, then there's really nothing you can do. You're going to have to allocate on heap, and you're going to have to cope with, the on heap allocation life. Okay. The only other thing you can do is start recognizing these allocation hotspots in your application and do things to actually to reduce them. So just to give a little summary of this is like a typical heap space where what we're looking at is Java heap. And Java heap is going to be made up of a nursery where all the allocations are generally going to occur, survivor space where the data is first copied to, and a tenured space where after it's survived a certain period of time, it's going to be deemed as old enough to actually be moved out into this tenured space. And each space here is going to contribute to a different set of problems, and all are going to affect GC overhead. But how we solve these particular problems is also going to affect the memory efficiency of our application. So if you look at a regular allocation, what we're going to see is that we basically have a top of heap pointer. And we have two threads here that are going to do things. So one's going to create a new foo and then a byte array, and the other one's going to create a new bar. And so we're going to watch the allocation here. So basically, as I start executing this, what I'm going to do is I'm going to grab the top of heap pointer, and I'm going to say, I need so much space. I'm going to allocate that much space. Now, if I do this on a per object basis, what I end up is basically having this top of heap pointer you have to have barriers around it because it's a contended value. and multiple threads are going to be altering it. So one of the things I can do to take the pressure off of this is I'm going to say, okay, I'm not going to just go out and get like 100 bytes I need for this foo. What I'm going to do is I'm going to go get a megabyte. I'm going to call that a TLAB. So let's call it a TLAB structure. Okay? And there's all kinds of rules about how TLABs are allocated, but effectively you can say that I'm just going to give that thread a megabyte, and it can go off and allocate into the megabyte for until it exhausts it. And when it exhausts it, I'm going to get another TLAB, and it'll continue to allocate that way till I run out of memory. Right? So we're going to get that TLAB being executed, and what I'm going to do is I'm going to now internally allocate the number of data, the amount of data that I need for foo, and then I'm basically going to allocate into foo into that space, as you can see here in the diagram. Then I have bar. He's going to do the same thing. He's executing also. He's going to get his TLAB. And of course, we're going to bump up the top of heap pointer there. And the only other condition we really have to consider, well, one of the other serious conditions is what happens with this byte array. Okay. Now, if the byte array is bigger than the TLAB, then basically what I'm going to do is I'm going to bump the top of heap pointer for it and do an open allocation here, right? So this is basically how the allocations are going to work when we're allocating on heap. The problem is when we get to the end of the TLAB, what do? Well, we're going to have a threshold here called a waste percentage, meaning that if I get so far down the pipe where I don't have a lot of buffer left over and I need to do another allocation, it's like don't bother trying, go off and get another TLAB in this case. And as it turns out, how you set the threshold can have some interesting impacts on the performance of your application, because if you're consistently getting into a situation where, for instance, you're not quite beyond the threshold, but you're going to overflow if you perform the next allocation, then in those particular cases, what you need to do is you're going to say, oh, damn, I'm going to allocate here, but I can't. Now I need to roll back and do some, do some extra calculations, and then go off and get a TLAB, right? So basically, this buffer here is to prevent, that threshold is to prevent buffer overflows. When we get into tenure space, there's a couple of different ways that this is managed. In copying evacuating collectors like G1, the scheme that is used in Eden is going to be sort of mimicked in tenure space. In what's known as in-place collections, we're going to manage things by dealing with a free list. Point is, when we put a free list in the mix, then the allocation cost tends to go up by a factor of about 10. So these allocations become a lot more expensive. Right? And anyways, let's look at some of the problems here. Yeah? So if we look at some of the problems, you say high memory churn rates creates many temporary objects, and that's going to quickly fill Eden, which means we're going to end up with a lot of frequent young GC cycles, which means that we're going to add a lot of tail latency events to our overall latency picture, right? Now, this frequent, so we are also dealing with this issue where we basically have two ways of measuring time within Java Heap. The first way is just like the regular way, it's wall clock. It's like, things happen over 10 seconds or 30 seconds. The other way is that we age data based on the number of garbage collections they survive, right? So say we have data that's temporary or temporal data, which means that we don't actually want that data to end up in tenured space, right? Say it lives for, 2 seconds. The question is that going to end up in tenured space? And the answer is, I don't really know. It depends on how many garbage collection cycles have run over that period of time. If I have accelerated my frequency of garbage collection, then there's a good possibility that stuff is going to end up in tenure space. If I have my garbage collector tuned so that I'm running fairly infrequently, then it's very likely I'm going to catch this temporary data in young generational space where it's cheap and easy to collect, right? But the other point is that this is just going to add to the allocation pressure because I'm also going to be copying the stuff. And of course, copying is yet another allocation. So the speeding up aging has a lot of downstream detrimental effects. You get premature promotion, so things go up before they should. We get more frequent collection of those spaces that we're prematurely copying data into. We're copying data more frequently, so we have increased copy costs. We tend to fragment the heap at a quicker rate, meaning that we need to deal with defragging in some cases quite more. So you can see the list of problems go on and on and on. And I think the last point is that allocation is fairly quick inside the JVM, but quick times a large number still takes a long time, right? Just a simple math. So when we say high allocation rate, exactly what are we talking about? So here's a chart we have sort of cobbled together by heuristics, come from tuning applications from a number of different industries all over the place. And really the red zone is anything where when you're in the red is like something above 1 gigabyte per second, so some magic number. And this doesn't really seem to depend upon the hardware that you're using. So it doesn't matter if I'm on a laptop or on a super duper whatever quad socket server thing. Actually, the quad socket server thing probably performs worse than the laptop in these cases. But the point is, as soon as you get above that threshold, what we find is that there's significant opportunities for improving the performance of your application by simply reducing the allocation rates. And that means finding where the allocation hotspots are and reworking the algorithms to make the application more memory efficient. Okay? By the time you get down in the green area, which is somewhere around 300 megabytes per second, then you can see basically this is like a power curve type shape, which means the opportunities at that end become much less. So, so the question is like, where do we get these numbers from? Well, we can get estimates of this by looking at the garbage collection logs. So by looking at the garbage collection logs, looking at the data there, doing some calculations across a number of different collections, what we can actually do is now sort out approximately what your allocation rates are. Okay? Now, large live data set sizes also come with their own issues. So the inflated live data set size is something that you see with session objects and things like that, things that are trying to maintain state, even if it's temporary, right? So it creates a condition which we call loitering. In other words, the data is going to stay in heap for a long period of time, which means it's likely to be pushed up into tenured space, but then it's going to go away eventually when the session gets timed out or closed down or something like that. Now, the problems we get here is that we get inflated scan for root times, right? So if you think about one of the things that we have to do in order to run the garbage collector is we have to find these things called GC roots. So these are the things that are by definition live for any memory pool that we're collecting. We have to find them. So we have to go through all these other memory pools and say, do you have any pointers pointing into that space? Right, that's what we need to. So, so we have this large live data set over here that may have pointers pointing into the space that we're trying to collect. Then I have to linearly scan that whole space. So then it's just, larger, takes more time because it's just this linear relationship, and that's all there is to it, right? You get reduced page locality, which has its issues, inflated compaction times, increased copy costs. There's generally likely less space to work in, and so there's a whole bunch of issues that come from this. Additionally, with the copying collectors, you can see this correlation, this clear correlation between occupancy and CPU utilization. So if you look at these two charts here, the one on the left, if you just follow where the red dots are, that's what's known as the live set size. And with the live set size, you can see that it's growing. And the one chart on the right, the red is like CPU utilization. And you see there's this very clear correlation between the live set size, and the overall CPU utilization. So you can see that you're just going to run your CPUs hotter in the situation where you have larger live data sets. Now, the other condition that we addressed in the previous talk here was like a memory leak, or what we call an unstable live data set size. You end up in the situation where you're trying to tune the application, right, for a condition that's always changing, which means that the way you should tune it will change, but you only get one shot at tuning, and so do you tune for the beginning, tune for the middle, or tune for the end? It's becomes difficult to understand where you're supposed to tune. So obviously you'd like to find these conditions and shut them down as soon as possible. Right. And I did do a little bit of talk about escape analysis at the beginning. And with escape analysis, what we're actually doing is we're trying to determine what is the visibility of a piece of data. If the data is completely only visible and proven visible only to a single thread, then of course there's a number of optimizations I can provide that might help me eliminate this allocation site. But if it's data that is escaping, in other words, that it's possible that other threads can actually see this data, then of course there's nothing I can do at that point, and I actually have to go through with the full unit of work. So obviously, how you scope your variables is very important. Very, very important. So if you can keep your variables local to a method, that's very easy to prove that that's not going to escape. If you make them, even if you make them just fields in your classes, it's possible they might not escape, but it's, that becomes less likely. By the time you're dealing with static variables, those are fully escaping. Right? So you can see one of the things you can do in your code to have an immediate effect here is just simply reduce the scope of your variables and just reduce them. Okay, so in this case here, we should actually see some of this in sight here. So I should actually have some sort of demo here for you. Now, I had some stuff running from the last talk that I just finished, just before this one, which I wasn't cooperating in the sense that it wasn't shutting down for me. So I do need to get that shut down, and that will help with the demo. So I'll just go over there. If there's any questions that people have, please feel free to ask them at the moment while we're working this out. Anything to start? No? Okay. So what I actually have here, I'll just pop it up on the screen here as soon as I get it opened up and running, is an application where, okay, sorry, my IDE has just gone nuts on me here. Ooh, that's weird. File, open, recent, which is going to be mastermind. Okay, here we go. We got it. So if I look at this particular application here and hopefully get it to run, what we should see is that it's going to be result in a high, very, very high allocation rate. Yep, and I am sharing it right now. Sorry, that's all. Thank you. And where'd it go? Okay, so here it is right here. So this is our little application. It's sort of like a game simulation thing. So, and let me just make it a little bigger so it doesn't really matter what's going on here. So basically what I want to do is I just want to run this test and have it run through. All right, okay. And we might want to do this one slightly backwards because it looks like it's in a funky state right now. But you can see basically this took like 4 seconds to run to get to an answer. And if I exit the thing and I start looking at the GC log, see where we are in terms of mastermind. Okay. No, sorry. Gonna run through here. Presentations. I might have picked up the wrong version of this, sorry. Next games. Okay, that's our GC log here and stuff like that. So let's do analysis. So there wasn't a lot of GC log activity in 4 seconds, as you can possibly imagine there wouldn't be. We are interested in this case in looking at the allocation rates. And you can see the allocation rates here are steady at about just around just about the 1 gigabyte per second. So there's still some opportunities for actually improving this. But what I'd like to do is I'm just going to abort this because, and go back if I can. So let's just, I'm going to uncomment some code here. And do that. I'm going to uncomment this code here. And that should actually, that's going to give some problems here. I'm sorry, I'm going to have to refresh this project. I ended up opening the wrong version of this particular project. But effectively what we're supposed to show is, well, actually, let's just go back to this one here. And I'll run it this way. And just see if we can find where the high allocation sites are in this particular case. So I'll run it again. And I'm going to just add some numbers to this one here. So it just runs for a bit longer. And I'll just do a visual VM. So I want to start with this particular one in particular sort of on purpose because this is a profiler that will actually inject code into the runtime. And as it injects code into the runtime, what it does is it actually disturbs the optimizer's ability to optimize things. So what you tend to see with this particular profiler is that it will, there's allocations that might have been eliminated, but because the profiler has injected code and has wrapped these allocations with code, and there's actually other threads that are processing the data, you end up with this situation where you fail escape analysis and you actually don't get the allocation site reduction that you normally would see. So if I look at this thing here, so I'm going to take a look at allocated objects and basically say, okay, this is a frequency count is what I'm looking for. So this is an approximation of a frequency count. So I'm going to go back to my application here and I'm just going to run the test. And we're just going to look at it and just see what actually turns up here. In terms of hot allocators. And is it running? Yeah, it's still running here. I'm not sure how long it will run for. But you can see very clearly now that the, whoops, okay, something's going on. Okay, so you can see fairly clearly now that the hot allocation site here is this like index object, you know, whatever it is doing. And sort of second behind it is this score object. Now the score object is actually quite an interesting, is the interesting case here. In the sense if we actually look at what the score object looks like, so if I come back over here and open it up, and we look at how it's defined, we can see that, okay, so I have a Boolean, an int, and an int. So there's like 3 primitive values right here, okay? Not only that, if you look at where it's actually used, over here in this board, you can actually see that it's inside this while loop. We're creating this new score, and we're actually using the score down here. But effectively, that score value does not escape the confines of this particular loop. So this is a non-escaping object. So if it's a non-escaping object, the question is, okay, so why is it showing up so big here? And of course, the answer is that, because of all this instrumentation, it now escapes, which means we can't do the allocation set reduction. So this is a particular case where, I could do the, the smart thing, which would be to take this out here, declare it up here, and then basically run, I guess, somewhere here like a score. Okay, so that would allow me to reuse the object, so I wouldn't be allocating anymore. But if I do this, you could say like, okay, wait a second, not good to have that thing being allocated in loop, and certainly the profiler proves that to us, right? But by doing this, if I run this application again, you're going to find that it makes no difference in the performance of the application because the optimizers are already going to have taken care of the problem for me. They're essentially going to hoisted that, eliminated that allocation site out of the loop. Okay, so in this particular case here, we can see that, so the index is really the problem. So what we can see is, where our index is being created, where they're actually being used in this case. And I can do this with a snapshot, and I can follow down here. And you can see that it's really a core part of the logic of the application. Okay. So whatever this thing is actually involved in, whatever calculation is involved in, it seems to be coming all the way up to here in terms of how it's being created with this like math function. So if you look at what the application is actually doing, it's calculating these 3-digit sequence because I said, okay, I want to guess whatever the sequence is. I have 100,000. Choose 3. So I want to guess, and I want to score the guess here to tell me how close I am, so I can filter out my next guess. But you can see what it's doing is actually creating a lot of these index objects as part of that calculation, and these index objects are actually what's the problem? So what we'd want to do now is actually go into the code and try to see what we can do to try to reduce the number of these index objects that are being created. So this is responsible for 500,000 of them. Actually, if we do a snapshot, we can stabilize the numbers. Oops.
So the assumption is here that because you've got so many allocations going on, your CPU is tied up in making allocations as opposed to processing data.
That's correct. That is the actual assumption. And in actuality, when you start making these, when you start improving the memory efficiency of your application, you're going to start actually seeing the biggest performance gains here. Okay? So, excellent. Yes, so I can go into the code. I can go into, I think it was called this arrangement group. And you can see that we are using indexes all over the place here. So what I can do is to now just actually walk through the code, do the analysis I need to figure out, okay, are there any reductions I can do here to try to maybe potentially reuse indexes or somehow change the algorithm so that I'm using fewer indexes than I had been. Okay, so we are at about, I guess we're supposed to stop at about 3 o'clock. It wasn't really clear to me. So we're about 4 minutes away from the end. So what I'd happily do now is take any questions that you have.
The instrumentation that popped into place.
Yeah.
It affected the optimizer.
Correct.
It affected the optimizer in being able to figure blue was not escapable.
Yeah.
So it caused it to hang around.
Yeah.
So for that, you ended up with a Y when you were looking at your chart, your analysis.
Yes. So just to repeat the question here, what we're actually seeing is that what happened was that since the instrumentation comes in and actually wraps the allocated object into another object, in order to do that, it has to pass it into a method that's part of the instrumentation. And as soon as it's done that, then it's basically a failed escape analysis, which means that we're not able to scale or replace that allocation, right? Like we would have been able to without the instrumentation in play. So, yes, exactly. It's exactly. At that point, it might as well be a static and everything like that. So there is a way to detect this. So what we do is we turn on the hotspot logging, and then we use a tool called JITwatch to actually do an analysis on the logs. And so part of what JITwatch will tell us is what allocation sites have been eliminated from the code, right? Or they might tell us that it hasn't been able to eliminate an allocation site, and it'll tell us why. So in those particular, so that's like a whole other talk to go through, but effectively, these are the tools that we would use to now come back and validate that what we're seeing from the profilers is actually true. Okay? Or the other case is, this is a case where we're actually using something like Flight Recorder, which does less disturbance of the optimizers, will likely give you the same type of answer. But since it won't prevent the, since it's not going to disturb the escape analysis, then you're still going to see what's known as TLAB allocations within Flight Recorder. And so the TLAB allocations are going to be the allocations that have not been eliminated. So those are the real allocations. Anything not allocated in a TLAB is going to be assumed to be like a scalar replaced. So you don't have to worry about it. Okay? So that's would be the nomenclature that you would see within a tool like Flight Recorder. Make sense?
Are the TLABs kind of like the regions?
TLABs are not like regions. You'll have hot allocating threads on the next garbage collection, after the next garbage collection, will be assigned larger TLABs or be able to allocate larger TLABs. And what you're going to see is that cold threads are going to be given smaller TLABs. Okay? So there is this elasticity in terms of the size of the TLAB. So it's not a fixed thing like a region. Okay. Any other questions? Or should I let you go off to enjoy the rest of the conference? Thank you for attention. And yeah, have fun. Thanks.